Hello guys, welcome back in my class with Miss Johanna in chemistry class IGCSE. So here what we have right now is a periodic table, and in this periodic table we have columns and rows. So that goes vertically we call column, and that goes horizontally we call rows. So in this case, columns and rows are actually showing the position of classification of elements in the periodic table. So such as this one here, the first column is showing what we call by group 1. So group 1, I'll just put G1. And then the next is group 2, the next column. And then this one here, we somehow in IGCSE, we haven't discussed it yet. So we go straight ahead to here, starting from boron, the column that has boron inside, we call group 3. And then the one that has carbon, group 4. And then the next group 5, group 6, group 7, and then group 8 at the end. Okay, but later on in AS level, we will learn about these groups that we somehow, as if we skip first, yeah? And this one, what we call by transition metals or transition elements. Okay, so here in group 1 and group 2, those are two groups that we call by metals. So group 1 is alkali metals, and group 2 are earth alkali metals. So when we see about the arrangement of the elements, as we know by now that the arrangement comes from the electron configuration of the elements. And we can review again a little bit. In every cell here, we have two numbers, the smaller one and the bigger one. The smaller one is what we call by atomic number, that shows the number of the protons or the electrons as a neutral atom. And then the bigger one is what we call by atomic mass, or we can also say it as nuclear number, because this number shows the number of neutron and also proton in the nuclei. Now, so it means here, let's say we take lithium 3. So it means that the electrons in lithium are 3. So it means if we configure according to the configuration that follows the arrangement of the group 8 or noble gas, so it means for 3 electrons of lithium, we will have 2 and 1. So it means that the first shell will have 2 electrons, and then the second shell will have 1 electron. So that's why the positioning of the positioning for lithium is in group 1, because it shows the valence electrons, yeah. And then it is in the second period or second row, because there are 2 shells that keep the electrons of the lithium. Okay, so after we know how is the background story of arrangement for putting certain elements in certain position, then we can actually also find out that there are similar properties among the members in one group. Okay, even actually we can find out several properties that become trends in reading this periodic table. What are they? They are the trends of atomic radii, and then electronegativity, and then ionization energy. Okay, probably we'll discuss one by one. Oh, and also reactivity. Yeah. Now, probably we'll discuss one by one related to the atomic radii. Atomic radii shows the distance of the nuclei to the outermost electron. So in this case, I'll take, for example, I'll take here potassium 19. It means that potassium has 19 electrons. So if I write down over here potassium 19, but first of all, let me just erase this one first. So I can have more space to write. Yeah. So here, let's say potassium 19. So it means for 19 electrons of potassium, then the configuration is the first shell will be occupied by 2 electrons, second shell will be occupied by 8 electrons, third shell will be occupied by 8 electrons, and then fourth shell will be occupied by 1 electron. So that's why the potassium is also classified into group 1 members, yeah, because the valence electron of potassium is the same as the valence electrons of lithium, which is 1. So they are all in group 1. Now, regarding the atomic radii, okay, if we see here, lithium has only 2 shells. So it means if we draw it here, let's say this is the nuclei. So it means lithium has only distance 2 shell far away from its outermost electron. That's for the lithium case. But then for the case of the potassium, potassium has four shells away, 4 shells away to show the distance of the nuclei to the outermost electrons. So we can say that the atomic radii of the potassium is bigger than the atomic radii of the lithium. So then we can also show by pattern or trends, yeah, here, that from the top to the bottom in the same group, then the trend of the atomic radii is increasing. Okay, so from the top to the bottom of the same group, once again, the trend of the atomic radii is increasing. Okay, now related to the ionization energy. Ionization energy is energy needed to release the outermost electron from its shell. So for example, if I want to show the equation of how the first electron released, okay, I mean to show the first ionization energy, but the first electron release is actually from the end, yeah, from the outermost shell. So it means I will say in the case of let's say in the case of potassium, I would say potassium, okay, usually it's not usually, it is actually measured as it is in gas. So potassium gas will releasing uh, 1 electron plus potassium positive gas. So this is how the energy is measured in this kind of reaction as it is in gas. So in this case, it means that the one that is released is the outermost electron. So with the more distance from the outermost electron to the nuclei, okay, of course, it is easier for potassium to release its electron because the attraction from the nuclei toward the outermost electron is smaller in terms of the further distance. Remember that the electrons move in the shell because there is attraction from the protons that are found in the nuclei. So that's usually what we call binuclear charge. So in other words, as the atomic radii once again, as the atomic radii increase from top to the bottom, what happened is the first ionization energy, so we say the first ionization energy, or usually we say IE1, ionization energy 1, is decreasing. Okay, so it means that the nearer the atomic radii, the stronger attraction force toward the outermost electrons. So then it is required bigger energy in order to help to release the electrons. Okay, now how about in the same row? In the same row, it means that it has the same number of shells. So it means we don't have any problem with the distance if it's related by the number of shells. But what matters is as it goes from the left to the right, as it goes from the left to the right, as we know, the atomic number becomes bigger. As the atomic number becomes bigger, it means that there are more protons from left to right if we compare from different elements. So in that case, we can say with more protons, it means stronger attraction force. When it is stronger attraction force, then the atomic radii is slightly nearer. So it means from the left to the right, we can say that atomic radii is getting smaller in the same row. Yeah. And as the result, as atomic radii gets smaller, so it means ionization energy. In this case, first ionization energy, or what we call by IE1, will get bigger. Okay. Yeah. So one thing that we should remember that the trend of ionization energy is the opposite of the trend of the atomic radii. And then second thing we need to remember, in the same group as it goes from top to the bottom, it means that the number of shells are increasing. It means the atomic radii are increasing. So then the opposite, the ionization energy, in this case, the first ionization energy is decreasing. And then in the same row, as the number of shells are the same, so the one that play important role is the increase of the atomic charge, or in this case, atomic number. So then, as it goes from left to the right, the trend of the atomic radii is decreasing because it gets nearer to the nuclei with the increased number of protons. And then as the opposite, the first ionization energy is getting bigger or increased. I think that's all first for today. Thank you so much. So we'll meet again in other videos and keep on learning. Bye-bye.